Okay, so now that we survived the math, let's look at some cool applications of convolutional neural networks. So hopefully your brain isn't too dead by now, you're still a little bit awake, and now we can look at some fun stuff that we can actually do with convolutional neural networks. So the first one is image classification. This is kind of a standard one. We've been seeing it a lot in the past few days. So you take an image, and then you ask what category does it belong to. So you learn on a set of categories what these images might represent, and you train on large data sets, and you can get some kind of classification. And this is a very commonly used task for convolutional neural networks. So if you have some kind of data set of images with some associated categories, it turns out that convolutional neural networks are really good at doing this. Another thing that we can do is object detection. So classification is interesting, but it doesn't necessarily give us much information as to where these things are located in our image. So in object detection, what we do is we actually find a bounding box that says where our objects are located. So we find a box that says, here is our object, and we also try to predict what's inside this bounding box. So you can imagine that this problem is already a little bit harder. And we're going to look a bit more in detail later on today how we actually do object detection and how do we evaluate how it performs. Image segmentation is also a really cool application for convolutional neural networks. So in this case, what we do is we try to say, not only do we do object detection in our image, so where are things located in an image, but within the box, what are the pixels associated to these specific objects? So here we have a very neat example that uses Mascar CNN, which we'll look at later today. And so we have our neural network that's predicting where the cars are in an image or where the humans are in an image. But what's really neat is that given a box, it also predicts the pixels that are associated to these different categories. And one thing I find really, really cool is if you look closely, so we'll wait for this to loop again, but you see here we have a window, and there's actually the reflection of the car in the window, and it detects the car over there. I don't know if some of you saw that or not, so here, look a bit closely here on this window. Right? So these networks are very powerful and can really get some really interesting representations. And you can imagine how useful this could be in the context of, for example, self-driving cars. It turns out that these same algorithms can also be used in biology. So say you're a biologist and you're looking for nuclei in specific cells. It can be very painstaking to go find them all and annotate them. So there are ways to automatically annotate these cells using deep learning. And again, in this case, we're using the exact same algorithm that was being used to detect people, except that now we trained it on a data set that contained many different nuclei. And we're telling the network to look for nuclei in a cell. So a really cool use case for these kinds of applications, and there's the link here to go read the paper. This was published in Nature recently. So this is where we're at the point where we're starting to have these applications of deep learning that can be used by most people. So if you're a pathologist, you might not have too much knowledge of deep learning. And if you're really good at deep learning, you might have very little knowledge of pathology. Right? So we saw in the previous slide, oh, okay, really cool, we can annotate these nuclei, but that means that if you're a pathologist, you now have to learn a whole set of deep learning theory and learn how to code just to be able to do these things automatically. Well, now we're at the point where these models are getting fast enough and portable enough where they can actually be embedded directly into microscopes. So now a pathologist who's working can actually be aided by the annotations that the deep learning network is predicting. And as a user, you don't necessarily have to understand all of the implementations behind the CNN, but you can still use the rich representations you get. So if you have a slide of some kind of slice of cell or tissue, then there is on board a GPU which is connected to the microscope. And again, you could read the paper for more details. And it's able to do this image segmentation in real time. So as the pathologist is moving the images under the microscope, it can actually look through the eyepiece and see that the network is predicting certain structures. So this is a really cool kind of use case where deep learning and pathology can meet. A really fun one as well is CNNs can be used to help models learn to generate captions. So tomorrow you're going to look at natural language processing with Mirko. He has a really great slide deck prepared for you guys. And so what we can do is it turns out that we can combine both convolutional neural networks and natural language processing algorithms to then figure out how to generate captions. So here we have, for example, the example of a woman throwing a frisbee in a park. So this is a caption that was generated by our neural network. So the image, as you can see, is very much a woman throwing a frisbee. But what was really neat, shown in this paper, is that the network can learn to attend to specific regions of the image. So when the network is generating the word frisbee, it turns out that you can see that the network is focusing on the frisbee. And there have been many works published after this. It's a really interesting kind of use case. And again, this combines both convolutional neural networks and natural language processing techniques. Another interesting application is human pose estimation. So what you see here is that you have a convolutional neural network learning to not only figure out where humans are in an image, but to also associate a sort of stick figure model to the person. Right? So you have these people here, they're dancing, and the model learns how to best fit these stick figure models. So it has to figure out the relationship between an elbow, an arm, and not only find the people, but fit these models to people. And again, here I'm linking to different implementations. So you have some, this one also published by Facebook Research, where now they're using an even denser model of the human. So they're definitely harder to train because we have more data, but again, some very interesting work. And this one actually, they boast some real-time frame-by-frame detection. So I think if you look at the top here, it looks like they're running at about 10 frames per second. So pretty impressive stuff. So another interesting one as well is road mapping. So we have a lot of satellite imagery, and you can imagine that if you're trying to map roads, so for example, if you're Google Maps or even Open Maps, typically you have to have people manually annotate these roads. This could be very time-consuming. And in countries where maybe you don't have as many resources, this could be a very challenging and limiting factor. So there are more and more algorithms that suggest ways to automatically map roads based on satellite imagery. And again, we take the satellite image, we pass it through a CNN, and we get the CNN to predict these different lines that would kind of represent roads. And here also what we do is not only do we detect roads, but we also detect the shapes of buildings. So from a single 2D image, we try to infer the depth of buildings so we can then have the landscape of a city based on the kinds of buildings that are in it. So you can imagine how useful this could be for things like urban planning. So we focused a lot on images, but CNNs can also be applied to a wide variety of other kinds of inputs. So sounds is a really popular one. So say you want to classify sounds, how would you be able to classify them? So one typical way that's done a lot in literature is to use some kind of spectrogram representation. So a sound can be a very dense signal to analyze. So what we can do is that we can compute some features, which in this case you could consider as some handcrafted features, where we output some kind of spectrogram. So you've probably seen these kinds of representations before if you were dealing with sounds. And the neat thing is that what we can do is we can use these as images. So we then can use all of the architectures that we've been able to find for images and use them for other kinds of signals. And again, this doesn't limit itself to sound, but any kind of signal where you might be able to do some kind of transform, say a Fourier transform, or any kind of mapping that you can do from your signal to the spectral domain.